My name is Trevor Trinkino. I am a quantitative trader with Kirshner Trading Group down in Austin, Texas here. And this is going to be the third webinar of a series that we've done on machine learning for algorithmic development. Here are a couple of disclaimers from FXCM that we got to show. Today we're going to be going over tuning the hyperparameters of the model that we have kind of slowly begun to build in the last two presentations. And we will also, we've been working with a random forest in the last two presentations. We will, like I said, tune those hyperparameters, and I'll kind of explain what each different hyperparameter is and what it does. And then we will also look quickly at some code for building a neural net, which we'll run through fairly briefly just because it's a little bit more complex. And then we're going to kind of compare the results of these slightly different models. And we'll kind of talk about how I actually take these predictions and then build it into a live trading model when the time comes. So as always, feel free to put your questions in the question box. I will either get to them as I'm going through the webinar, or I will get to them at the end of the webinar. We can reference back to whatever people were curious about. All right, so hyperparameters. And a quick recap of what we have done in the previous two videos. Initially, we basically went into Quant, which is the kind of backtesting subsidiary of Kirshner Trading Group that I use to build and develop all of my algorithms, and is available to any user on the website if they just want to go to www.cloudquant.com. It gets you to this kind of backtesting homepage here, and any user can use Python to create their own backtesting engine and see how it does back to the beginning of 2011 on all US equity tick data. There was a quick question. The previous two webinars are on FXCM's website, I believe, and their YouTube channel, as well as on cloudquant.com. So if you have missed those, then you can go check them out. Anyway, so back to our hyperparameters. After we collected the data from Quant, we kind of, we collected the data in such a way that we built features and variables that we thought the machine learning classifier would be able to make decisions based off of. And I would again like to stress that this is the most important step of the entire process, is collecting the correct data, and collecting data that contains relevant information to the setup or the decision you're trying to make. But again, if you want to get some more info on that, go back to particularly the second webinar. From there, now that we have collected our data and we have kind of filtered down our features to a point where we are, we know that we've collected data that allows the machine to make a decision on and to split our samples and our trades correctly into profitable and not profitable trades. The next step of the process is tuning these hyperparameters. And what hyperparameters are, they are just slightly different settings, if you will, or tweaks to each different machine learning algorithm that will tell it to learn by a different set of rules in some sense. Random forest is just a group of decision trees. So a lot of the hyperparameters involved with decision trees that we will play around with are max depth, number of estimators, and minimum samples per leaf. The maximum depth will just limit the maximum number of decision boundaries or nested if statements in each rule set. So if we, if three of our variables that we collected were the average volume for the day, another variable was the overnight gap as a percent of ATR, and then the third variable was volume traded in the first 10 minutes divided by the average volume maybe multiplied by the price move in the first 10 minutes, percent price move. If we had those three variables, then, if we had a maximum depth of 3, we could potentially have a decision tree that says if average volume is greater than X, and if the gap is less than Y, and if this third volume and price movement variable is less than Z, then that would be our kind of nested rule statement and our our nested if statement and one rule set. If we had a maximum depth of 10, it could be something that would go to the extent of if average volume is less than X, if gap is less than Y, if our volume and price movement variable is less than Z, if also variable 4 is less than J, if average volume again is less than H. You can kind of see the pattern all the way down to 10. So, as we allow the maximum depth to be deeper, it creates a more powerful and more complex machine learning algorithm and allows the machine to find more subtle patterns and dependencies on the different combinations of variables and features. But to that, the downside of that is it can also overfit the data pretty easily. Normally, when I'm working with market data, it is extremely noisy. So my typical range will be anywhere from 3 to 10. The next kind of hyperparameter here is called number of estimators, and that is just the number of decision trees we're going to group together into our ensemble. If you have a lot of these, you can normally get away with a slightly deeper max depth because each different decision tree is going to sample a different subset of the training data. So, each different decision tree is going to have a slightly different rule set. And this is one of the reasons why random forests are so powerful and easy to use right out of the box, is by creating these different subsets of trades and these different decision trees, we are really preventing overfitting, or the random forest is much more robust to overfitting because it's going to create slightly different rule sets the whole time. It's not just going to fit the entire data set to a singular decision tree. Number of estimators, generally the better, or it's better to have as many as you can. You definitely don't see too many improvements when you get more than 1,000 or 2,000. Normally I will have somewhere from 100 to 500. Again, this is just another hyperparameter that you kind of have to tune. Sometimes more is not necessarily better. And then the third one, which is again just kind of preventing the complexity of the model and constricting how overfit the model could be, is minimum samples per leaf. So if we think about starting out with maybe 1 million trades, and that is the data that we are going to train our machine learning classifier on, and we have got say we don't set the maximum depth parameter, which random forest defaults to none, which means it will go as deep as it possibly can until it hits one of these other minimum samples per leaf or another hyperparameter constraint. But basically, if we did not set the maximum depth, the decision tree would build and build and build and get deeper and deeper and deeper until we only had, say 50 samples left in one node. And if we had, if it tried to split that node again and it couldn't put 50 samples in each one of those resulting nodes or child nodes, it would not split anymore. So it would stop at that previous node that had more than 50. And that, like I said, prevents overfitting because it forces the random forest and the rule sets to at least have 50 different trades that support that rule set, or it's not finding subtle patterns in 5 trades per se. It's going to force the machine to find patterns that are present in at least 50 trades. Most of the time here, I will be anywhere from 100 to 1,000, but it's very dependent on the total sample size. if you have 1 million trades, you're probably going to want to have at least 1,000 minimum samples per leaf in each node. If you're only working with maybe 50,000 trades, then you're probably going to be closer to the 50 to 100 minimum samples per leaf. All right, and then another algorithm that we've spoken about briefly is the gradient boosted decision tree. This is the algorithm that I use probably more than anything else, just because it is, again, like random forest, it's pretty easy to work with right out of the box. It's pretty robust to overfitting, and it is slightly more powerful. The one thing that the gradient boosted decision tree does that a random forest does not is it builds its trees in succession, and it basically has a loss function that it tries to optimize from the previous tree. So in some sense, it learns where the previous estimator or previous predictor went wrong, and then using gradient descent tries to slowly tune the next model so that it will minimize the previous model's loss function. And the way it does that is through this learning rate. Again, by using gradient descent, it will kind of update the weights or update its loss function as a percentage of this, based on this percentage of learning rate, if that makes sense. Normally, if you have a larger value here, is going to create a more powerful model, but it's also going to overfit a lot easier. So my typical range is the 0.5% to about 10% here. Normally landing around the 1 or 2% area. With learning rates in general, you normally want to test them out on a logarithmic scale. So, if you're trying different learning rates, you would probably try 0.1, 0.01, 0.001. You wouldn't go 0.1, 0.2, 0.3, 0.4. And that will allow you to search the hyperparameter space a little bit more efficiently. Okay, for neural nets, which we'll get into briefly here, and I will kind of show some code quickly, and I'm happy to share that code with anyone who is interested in playing around with them more. I will include my contact information at the end of this webinar. If anyone wants that code, I'm happy to send it over to them. Just shoot me an email. But anyway, neural nets have a much larger number of hyperparameters and parameters in general, which is, they are extremely powerful. In general, they're probably not as good bang for your buck if you're just getting into machine learning. They are much more complex to set up. There are a lot of ways that they can, they're much more finicky in some sense. You really have to have some experience, and one slight tweak in the model can make a dramatic difference. Whereas the random forest and the gradient boosted decision trees, if you tweak a hyperparameter and it's not perfect, it's not going to completely ruin the model. It's still going to perform pretty well. Whereas a neural net, it could, it won't completely ruin the model, but it could dramatically change your results. So a lot of the hyperparameters that you're going to deal with there are just the number of hidden layers, the types of those hidden layers, whether it's going to be, today we're going to look at a long short-term memory cell network that is followed by some fully connected layers. From there, you have the number of neurons in each layer, the different activation functions within the layers, learning rates, momentum, regularizers. It goes on and on. I will briefly go over kind of some of the standard settings for the neural net when we get there. But again, neural nets are really popular right now and do an incredible job of engineering features within them, which is something that random forest and gradient boosted decision trees do not do. So neural nets, that's probably the reason why they're so popular right now, is because you don't have to inherently do as much feature engineering before tuning the model. You kind of just need to give it data and then spend more of your time tuning the model and tuning these hyperparameters so that it can efficiently create features. All right, so we are going to hop into some code here in a second, but basically before we do that, we need to kind of think about, as we're running through all these different hyperparameters, the best way to kind of test this is, say we've got, and this is the exact same Jupyter notebook that we've been working with throughout this webinar series. Up here we have loaded our data in from Cloud Quant, which is just from this trade. We collected a bunch of data in Cloud Quant at our potential entry event and just downloaded that trade as a CSV file and then loaded it in here. Again, if people would like to get some more info on what's going on within the first few cells of this IPython notebook, take a look at the first 2 webinars. So we have split our training data into the correct date ranges. Again, as we spoke about, especially in the first webinar, you need to train your data or train your machine learning model on data before a certain date, and then test it on data after that date, and then probably leave some sort of validation set out, which is the most recent 4 months, to kind of test your model finally after you have tuned all the hyperparameters, just to make sure that you're truly getting an out of sample test and you're not overfitting your data to, you're not overfitting your model to the data and then getting biased results, basically. So right here, we have split our data into our different training and testing. Here, we're just kind of replacing the null values with the median of that column. All right, this would take a while to run, but basically what I've done here is I've just very easily created 3 for loops that are just looping through the different possible hyperparameter combinations, and then fitting each one of these different models with these slightly different hyperparameter combinations to our training data set, and then making a prediction on our test data set. And from there, we need to assign a metric to each one of these different combinations of hyperparameters so that we can judge how well those hyperparameters did. So getting back here, like I was saying, we need to create we're going to create a slightly different model for each different set of hyperparameters, and we are going to loop through each different ones of these models and make the prediction, and then we need to judge how well that model did, or how well that set of hyperparameters did. And this can sound like a pretty simple problem at first, but it's actually fairly difficult, just because each different metric in its own sense is going to get you slightly different results. A lot of the metrics for classification that I use, my two favorite are negative log loss and area under the curve. If people would like to research these a little bit more or get some more information on them, I would recommend going to Scikit-Learn classification metrics, and it will, right here. Scikit-Learn is developed by Google. It is the kind of machine learning package that we've been using throughout this webinar series and has excellent documentation. I would recommend everyone kind of start there as they are beginning this machine learning venture. But anyway, so we go back in here. Negative log loss, I like that just because it will penalize the model more for being overly confident in its wrong trades, if that makes sense, and it will penalize it less for being slightly less confident in its wrong trades. And the way that the model is or confidence is judged is back over here in our Jupyter notebook. We can either call clf.predict, which is a function in the random forest class, and that will give us a 0 or 1, which basically matches our binary label that we set up here. and that is just going to predict whether each one of these trades is going to be good or bad based on, you know, what we told it, what we defined as good or bad up here. What negative log loss will do is we would actually call predict proba, and it would predict the probability of that trade being good or bad. So negative log loss actually takes into account that probability, and like I said, will penalize trades or predictions that it was very confident on but got wrong. And then area under the curve just looks at the, it is the kind of percentage of false positives and true negatives, or opposite of that, and will more or less, you know, it's going to, the model or the metric will be higher for the number of true positives and false negatives that it correctly predicts in some sense. So it's just looking at your binary classification there. But the reason why I use that as opposed to maybe an accuracy metric, which is in some sense what people would default to, is because if you have unbound classes, so say you've got 100,000 trades and you labeled 25,000 of those trades as good trades and 75,000 of those trades as bad trades. If you use accuracy as your metric, then the machine learning model could effectively learn to just predict every single trade is bad, and it is going to get 75% accuracy. So we don't want that, obviously, because the machine isn't actually learning anything. It's just exploiting a hole in your code that you have told it to learn accuracy. And in most cases, you're not going to achieve better than 75% accuracy on market data. For other machine learning tasks and signaling tasks, you probably, you know, there's a good chance you will, but because market data is so noisy and it's so difficult to make these predictions, you're almost never going to get better than 75% accuracy. So the model is just going to learn to predict no on everything, which doesn't help us. And what area under the curve does is it can deal with those imbalanced classes because it's just looking at the kind of percentage of true positives and the percentage of false negatives. You know, so it can kind of weight those classes equally in its metric. Another one that I use a lot is precision, which is just looking at the percentage of true positives over the, it's basically how many times if the machine predicted that a trade was good, that the trade actually came out good, if that makes sense. And then recall is, if you're thinking in terms of baseball, it would be, you know, for every strike that was thrown, how many times did the batter hit that strike? And then F1 is a weighted average of these two. So the ones that I would default to for you guys would be negative log loss, area under the curve, and F1, with the knowledge that negative log loss, if you were using it, you would have to do predict proba here instead of predict. But basically what we're doing here is we are just looping through a bunch of different combinations of these hyperparameters, calling predict on our testing data, getting our metric, and then saving that metric in a dictionary that also has our hyperparameter string as the key. So after we would hypothetically run this, it would probably take all night to run because there are so many different combinations of hyperparameters here. We could then look at this dictionary and we could sort the values by the highest metric, you know, our highest area under the curve scores, and see what hyperparameters resulted in that score. There are ways to kind of search this hyperparameter space more efficiently using a genetic algorithm or other similar techniques. You know, I'm not going to get into exactly how to do that, but basically you could think of it in a way as, in this simple for loop, as we are running through these different combinations of hyperparameters, you know, say after we ran through 100 combinations of hyperparameters, we would then look back and see, okay, out of all the different maximum depths, you know, where in our maximum depth distribution are we on average getting the best results? And maybe for the next 100 hyperparameters, we're going to kind of focus our, or bias our, max depth parameter towards that area of the distribution. So as we're searching through these, hundreds, sometimes thousands of different hyperparameter combinations, we will, at different iterations throughout that search, kind of go back and look at our results and then change our search moving forward based on the previous results, if that makes sense. And that's not exactly a genetic algorithm, but would be a simple way to kind of use this for loop to learn a little bit more efficiently. And I will share the Scikit-Learn documentation link at the end of this webinar, and there is going to be a recording of this session. It will be up on the FXCM YouTube channel here probably by the end of the day, as well as on Quant. All right, so once we've done this and we have our dictionary and we've found the best metric and best combination of hyperparameters, we would then go back to our validation set, which would be, in my case, has been since January 1st of this year. And we would train our model with the optimal hyperparameters based on this, these nested for loops. And we would make predictions on the validation set since the beginning of the first year and make sure that things looked correct. So, make sure that our model didn't just overfit to the training and testing data, but it actually generalizes well out of sample as well. And if we go back here, let's see, this is, where is it? Done for your test. This is the, this is the one. So this is the back test that I got for the model that we had built. And again, this was, explain the model a little bit in the first webinar, but it is more or less a multiple days of descending closes. And then we want just a very large kind of puke, and we're going to fade the position and go long and kind of wait for the reversal back up is the idea. So this is the, and I actually have this model running in live. This is the backtest simulation that we got after running a random forest through our hyperparameter, through this for loop and tuning all of our different hyperparameters. We're going to jump into a neural net quickly here. So here is the code for a neural net. Again, it's much more complicated. I'm using TensorFlow here, which basically forces you to, it's a lot more abstract than Python or Scikit-Learn, and again, would not recommend people, if they're just getting started, jumping into the neural net. Like I said, I'm happy to share my code here. This is just a recurrent neural net with how many? Let's see, I believe we had 2 layers of 16 with LSTM cells, and then I think it led into a layer of, I think it was just one fully connected layer with 10 neurons in it. And I'm using, and for those of you who know neural nets, I'm using an atom optimizer, using the LU activation function, using batch norm, and then using key initialization for all the weights and biases, for those of you who know. Again, one of the reasons why neural nets are so powerful, like I mentioned, is you don't need to inherently create features. So, back over here in our Jupyter notebook, when we went up and we created our different features here, we had to go through and based on what we had done in the previous couple webinars, you can see that this random forest classifier can rank its feature importances. So it will align the total information gained from including each feature in the model as a percentage of the total information gain of the model. And you can kind of see what features are more important And then from there, you can have that kind of direct your feature engineering step. What we did with the neural net is you more or less feed in just kind of like the base of these features. So here we can say day range is ATR. There's a lot of features here where I'm combining movement and volume into my own variable, kind of making dummy variables based on that, because the random forest classifier cannot inherently combine those features. It can create dependencies on different features, if this and if that, and if this, then that, but it cannot combine bar range 15 and bar range 60 and create some sort of new weight based on those two features, which is what a neural net can do. So a neural net would take all of these features and it would feed it into the next layer of neurons, and it would combine each of these different features in different ways to kind of learn different non-linear dependencies that each feature may have on each other, and create new features based on the data that we gave it. And then specifically what a LSTM cell does is it's short for long short-term memory, and it is a type of recurrent net which has been used previously for a lot of voice and speech recognition and natural language processing, because it can learn the concept of time, and it has these different gates within it that will basically allow it to remember and forget as it's moving through the time series. So it can if you have a time series of say 100 bars, it can learn what was going on in the first 5 bars and carry that information all the way to the last bar when you're ready to make your prediction. And I do, there was a question if I've used these for predictions and for models. I do have a couple models that are using LSTM or just a regular deep neural net, normally trained or pre-trained with an autoencoder or an RBM. I do have 2 models that are using this right now, 2 or 3, and for certain problems, they work better than the gradient boosted decision trees, especially if there's a lot of data. Neural nets can kind of continue to learn, and they can learn non-linear decision boundaries. And in those, those models, I was able to get better prediction quality out of the neural net. For a lot of models, I'm not able to beat the gradient boosted decision tree with a neural net. And the reasoning behind that, I would think, is one, there isn't quite enough data for some of these specific trade setups. Like our model over here that we built, I believe has number of trades 4,700. And I think that before, that's obviously the number of trades that it took, but I think I was initially training this on 100 to 150,000 trades, which in this case was not quite enough data to really take advantage of the neural net. And then the other thing too is just the resources. It takes some more, it takes GPUs and sometimes clusters of GPUs to train these deep neural nets quickly. So, I use AWS a lot online, but it takes more time and more money to kind of run through your hyperparameter search of a neural net, because there are so many different weights and so many different biases and so many different hyperparameters within a neural net. Your nested for loops become much, much longer, and you cannot efficiently search the entire features or hyperparameter space. You need to either do it randomly, or you need to use something like a genetic algorithm, which is what I do, that learns, basically will create a bunch of different models randomly, and then we'll kind of crossbreed the best models to create the next generation of models. So anyway, that is, again, here's some code. If people are interested in, playing around with this code or, doing some work with neural nets, I am happy to send it out. Like I said, this is just a class-based model that more or less allows you to pass in the number of recurrent layer sizes followed by, a list of fully connected layers. Then you can pass in a list of dropout percentages if you would like. You can change the optimizers, whether you can change to different LSTM cell, all of that jazz. So if people are interested, shoot me an email. But anyway, so back to our kind of initial workflow here. Once we have found the model and the combination of hyperparameters in our Jupyter notebook that gives us the highest metric score, we will then either save this little CLF object, which this CLF object has all of the rules and the nested if statements saved within it. So this CLF object, we can save it as a pickle file, and it will, it'll save our model, and then we could, in Cloud Quant, it's pretty easy to go over here, and if we just import pickle, we are able to basically upload that pickle file, which again has all of this entire model and all of the rules saved within it. We would upload that pickle to our user data here, and then we can read it in as a file and kind of reload this CLF object. So then, in the future or during a back test or live trading, at the exact same moment where we would have previously captured all of our data and then just written that data to a file, we will now capture all that data and then feed that data into our CLF, into our classifier object here, and call predict on it, and it will spit out a value, 0 or 1, or if we did predict proba, it'll spit out a float value between 0 and 1. And based on that prediction or that value, you can then make a decision. So, if we fed all the data in as this, stock is kind of puking and dropping and we're looking to fade it, we fed the data in and it gave us a 0.6 probability of it rebounding 40% or whatever we labeled the data as. We could then decide to make a trade if that predict proba returned a value greater than 0.6 or 0.7 or 0.5. That is just another, in some sense, almost just another hyperparameter that we would have to tune in our greater model. And then in our live trading environment, we would do the exact same thing. We would just kind of load in this classifier object at the beginning of the day before we turned on all our models, and throughout the day as the data is coming in through our systems, we would collect that data when the entry event has happened. We would feed it through this CLF object, call predict on it, and it would spit out a 0 or 1, or like we had just spoken about, a number between 0 and 1, and we can then make a decision on it. A similar, you would do the exact same thing for a neural net here. This code is more or less what is just given to you in the Scikit-Learn random forest class. This is just me kind of recreating it for a neural net, but a neural net would just call this, we would save this TensorFlow graph and this TensorFlow model to a file, and then we would load it up. We would kind of restore the TensorFlow graph and the model. And again, I'll provide some information at the end of this webinar if you're interested in learning more about TensorFlow and where to start, but it definitely takes a little bit more experience and knowledge to work with these as opposed to the random forest. But we would kind of restore our graph and all of the weights that we saved for all the different connections between the neurons. And then we would just make our prediction. similar to how we would do with the random forest. And based on that prediction, we would either take a trade or not take a trade. Yeah, so that is more or less the process. I believe this graph right here was after we had tuned the hyperparameters of our model using a random forest. So we can see we've got a Sharpe of 1.6, a Kalmar ratio of 4.36. The Kalmar ratio is basically the same thing as the Sharpe ratio, except it is not penalizing for upside volatility. So it will only penalize the model for your downside volatility, basically. You know, like right here on this, you know, on these very large winning days that we randomly have, you know, that is actually going to make our Sharpe ratio lower because it's going to add to the, well, it could make our Sharpe ratio lower in some sense because our standard deviation is going to be so much larger. Obviously, our returns are also going to increase, but it's going to penalize the standard deviation, whereas the Kalmar ratio this day would not penalize the standard deviation because it's to the upside. So a lot of times I will look at the Kalmar ratio and then our net edge per share. I think if we go in the model that I am actually running right now is a gradient boosted decision tree. And this is the model with the tuned hyperparameters. So our previous Kalmar ratio was a 4.36 with an edge of 9, I believe. So now we've got a similar Kalmar ratio, 4.36, but our net edge has gone up from 9.6 cents to 14.3 cents. You know, so our overall return has increased almost 50% on a net edge per share level. And again, this is just from changing from the random forest classifier to a gradient boosted decision tree, which is this model down here. I use light GBM for my gradient boosted decision tree predictions, and you know, it's just a package that I use. Scikit-Learn has a gradient boosted decision tree as well, but it cannot run in parallel, so it takes a lot longer to run. Whereas light GBM and XGBoost are two of the kind of common gradient boosted decision tree libraries. They can run in parallel and they run much quicker. This gradient boosted decision tree actually trains quicker than my random forest does. And what I mean by running in parallel is just up here with the random forest. Say we've got 100 estimators, so we're building 100 different trees. Random forest, if you set n jobs equal to -1, it's just going to build a different decision tree on each different core that it has available within your computer. You know, so down here, when we do number of threads equals -1, because with the gradient boosted decision tree, it cannot build multiple decision trees at the same time. It needs to build them one after the other to minimize the loss function from the previous decision tree. The way that it can split this workload over different cores is that it looks for the optimum, you know, the best threshold and the best split threshold from different features over those different cores. So it's really building one decision tree over, you know, 5, 6, 10, however many cores you have in your computer, just by searching for different thresholds and optimal threshold for your different features on each different core. There's a quick question about, do all these features, indicators work for forex? And yeah, I mean, this process definitely works for forex. I know people who are using machine learning for forex successfully. You know, the biggest with any, whether you're trading US equities or foreign exchange, or just doing a regular machine learning problem, the biggest challenge you're going to have is creating the data and creating the features that are most useful and allow allow the machine to do its job and split on that data. You know, so here we, based on my trading knowledge and, you know, the trading knowledge of my boss and the other discretionary traders who have been here for years and been very successful, we will sit down and go over what they look at when they're getting into a trade and what they want to see, and we will then create data and create features that can kind of paint that picture to the machine. We won't explicitly tell the machine, okay, we need the volume to be greater than 10% of the average volume in the last minute. But we will give the machine the data to kind of find that optimum threshold on its own. So, we would give it a data point that is just, the volume in the last 10 minutes as a percentage of average volume. And then from there, the machine can go and find, do we want it to be 10% of the average volume? Do we want it to be 7% of the average volume? Do we want it to be 20% of the average volume? Whatever is optimal combined with the other different features that it's splitting on. So, for forex, I'm sure there's going to be some slightly different indicators that you would think about. I think a lot of the technical and price and volume indicators would probably translate very well from U.S. equities to foreign exchange, but including some more fundamental data would probably be useful with forex, and is useful with U.S. equities as well. It's just going to be slightly different types of fundamental data. And with Cloud Quant and Cloud Quant AI, which is kind of our new platform that we're building, we're going to more or less create we're going to have a Jupyter notebook built into the website here that allows direct access to all types of fundamental and sentiment data. So you can create features based on previous earnings or earnings beats, and all the different Morningstar data set is what we're integrating right now, as well as some of these natural language processing sentiment data sets like Alexandria or Ravenpack or SMA. So again, if you were to follow this process with forex and you were to find the features that you thought to be most useful and collect that data, and then once you had collected that data, gone through the process we spoke about in the second video a little bit, and boiled down the features to your top 20 or 30 that were most important, and then from there either created more features that you thought would help the machine do a better prediction, or moved on to this hyperparameter search and built your model, or built many different models with your different combinations of hyperparameters to get your most optimal metric here. That process would work. That is just kind of a data science machine learning process, not necessarily a specific US equities prediction process. Yeah, that is basically all I've got for you guys here. A couple other things just to mention. When we are searching through our different hyperparameters, we need to come up with our correct metric, as we spoke about earlier, whether that's going to be negative log loss or area under the curve, which is what I would recommend. You could also, calculate your Sharpe or Calamar ratios for the test set and see, kind of optimize a Sharpe ratio. And you could tell the machine to find the hyperparameter combination that optimizes your Sharpe ratio the most, or you could tell it to find the hyperparameter combination that creates the largest P&L, things of that sort. For regression, which is just when we're trying to predict on a continuous scale instead of a discrete scale, mean squared error, mean absolute error are kind of the two go-tos there. And again, they will get you slightly different results based on which one you choose. And once we have, one of the things that I have found to be useful is, instead of back here when we call our predict function, instead of calling predict on the entire training data set, I will kind of subset this into 5 or 10 different time periods and call predict on each one of those time periods, and then get a different score for each one of those time periods. And back over here, based on that, I will now have 10 scores for each hyperparameter combination instead of just one score. And with those 10 scores, you could do something like a t-test, and you could find which one was the most statistically significant. Might get you slightly more robust data as opposed to just judging the score as if it was all just one time period. The other thing I will do sometimes is I will take those 10 scores and I will look at what the worst time frame was, and I'll try and optimize that worst period. So as to, that's more or less just trying to optimize my drawdowns in some sense, or optimize the worst part of the predictor, which will normally lead me to having a slightly less complex machine learning model that will translate better into the live environment when we actually start trading it. All right, and here's just my contact information. Again, cloudquant.com is the kind of backtesting engine I use internally here, and all the quants use internally. And you can go to, by just typing in www.cloudquant.com. If you create a model and backtest it and it looks good, we will allocate you money and basically give you a split of the profits. I think we've allocated 72 million in the last year and a half. Might be 92 million actually now. So if you're interested in doing that, go for it. We're also building CloudQuant AI, which is going to be this kind of integrated Jupyter Notebook platform that will allow you direct access to all of our data files, and will allow you to really kind of dig in and do some data science and machine learning very quickly. All right, just had a question about forward testing. Yeah, so after we, once we get a back test that looks good and seems to be testing out of sample well, we're not just going to throw it immediately into live. We will forward test it, kind of a paper trading account probably for a week or two. And the biggest things that changes between live and back testing, and it's hard to replicate this in forward testing as well, but obviously you're going to move the market if you are coming in with big position sizes. You're also going to get partial fills, so sometimes there can be bugs in your code that you're not aware of just from getting partial fills on a position, little things like that. So we'll forward test it for about a week to make sure everything is matching up. And then, we'll start with relatively small size in our live trading environment, and then kind of build up from there as it continues to look good. Yeah, so that is basically everything. Kirshner Trading Group, again, is the kind of parent firm and the firm that I work for. This machine learning textbook, Hands-on Machine Learning with Scikit-Learn and TensorFlow, is definitely the best book I have found. It doesn't really look at financial data in any way, but as far as just machine learning knowledge and presenting it to you in a nice end-to-end format that you can kind of get the full picture from, and also exposing you to not only random forest and neural nets, but a lot of different types of machine learning algorithms. This is the best one to use. And then Amazon has this book called Advances in Financial Machine Learning, which is specifically a machine learning textbook built for, I believe, I don't know if it was U.S. equities. It was specifically for financial markets. It's been written by a guy who's managed a few multi-billion-dollar quantitative funds, and is probably the only of its kind I've seen out there, and really, really helpful. And then from there, online classes can give you basically everything you need for the machine learning knowledge and information. That the Scikit-Learn documentation, if you just Google sklearn, it will be one of the first things that pops up. And there are, it's a massive amount of documentation. It has its own custom Google search here. But what I would recommend is probably buying this first textbook here, buying a couple online classes, and then kind of going through them and going through this textbook, and it will reference Scikit-Learn in the textbook and probably most of your online classes as well, and just kind of reading the documentation for each different applicable model or import that you're using as you need it throughout the textbook or the class. And then from there, as always, if you have any questions for me or are interested in learning more about Cloud Quant, feel free to reach out. You know, again, if you would like to get a copy of this code for the neural net, I am happy to send it to you. I don't know if it's going to make a whole lot of sense, or you will be able to just kind of jump into using it immediately if you don't have some experience with TensorFlow. But this textbook, this first one here, the entire second part is all about TensorFlow and how to kind of build neural networks. So again, thank you guys for spending the time this morning. And one more question. So we had a question saying, do you have drag and drop decision trees, or do you have to write them one by one? So basically with this classifier object, it's going to create however many decision trees you pass in for this any hyperparameter. So say we pass in 100, it's going to save all of those decision trees just within itself here and within its kind of self object. And then when we save this CLF object here, we will be saving all of those decision trees. So we won't have to rewrite them out in our model anywhere. All we would do is just, you know, in Cloud Quant, it would be, where would it be? It would be in this, you know, on strategy start, which I'm not going to go into too much information about, just kind of our logic here. But if you have questions over in this documentation page, you should be able to kind of get the gist of our system. But basically just on strategy start, which is called right before anything happens on the model, you would just kind of reload this classifier object right here that has all of the decision trees saved in it. So you wouldn't actually have to write out any of the decision trees in your model. All right, guys, thank you as always, and feel free to shoot me any questions you may have. You know, I'm happy to help and share any code that I have built or used.